Steam blanketing damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of steam blanketing. Based on API 571. The operation of steam generating equipment is a balance between the heat flow from the combustion of the fuel and the generation of steam within the water wall or generating tube. The flow of heat energy through the wall of the tube results in the formation of discrete steam bubbles, nucleate boiling, on the ID surface. The moving fluid sweeps the bubbles away. When the heat flow balance is disturbed, individual bubbles join to form a steam blanket, a condition known as departure from nucleate boiling, or DNB. Once a steam blanket forms, tube rupture can occur rapidly, as a result of short-term overheating, usually within a few minutes. Steam blanketing damage refers to a specific type of failure that can occur in pipelines, vessels, or other equipment that handle steam or high-temperature fluids. This phenomenon arises when a layer of steam accumulates over a liquid or solid surface, effectively insulating it from the heat source. While steam has beneficial properties in certain industrial applications, steam blanketing can lead to significant operational issues and material degradation. Key aspects of steam blanketing damage. Number 1 is mechanism. When steam condenses on the surfaces of equipment, it creates a layer that prevents efficient heat transfer. This lack of heat transfer can cause localized overheating in the structure or components, leading to thermal stresses. Number 2 is material concerns. The materials typically used in construction, such as metals, can be prone to damage when subjected to uneven heating. The resultant thermal expansion can create stress that either leads to cracking or induces fatigue in the material over time. Number 3 is corrosion risk. The moisture and heat in the presence of steam can contribute to various forms of corrosion, including pitting and stress corrosion cracking. The condensation of steam can create an ideal environment for corrosive agents to attack the metal surfaces. Number 4 is safety hazards. Accumulated steam and the potential for subsequent pressure builds can pose safety risks, including catastrophic failures, leaks, or even explosions in extreme cases when equipment experiences a sudden rupture. Number 5 is operational issues. Steam blanketing can lead to inefficient operation of boilers and heat exchangers, causing reduced performance and increased energy consumption. It may also result in unexpected downtime for maintenance and repairs. Number 6 is prevention strategies. Effective management of steam systems, proper design and installation of thermal insulation, and adequate maintenance practices can help mitigate the risks associated with steam blanketing. Regular monitoring for signs of thermal stress and corrosion is also crucial. Steam blanketing key features and causes. Number 1 is steam layer formation. When steam comes into contact with a cooler surface, it is expected to condense. However, if the cooling surface is obstructed or if non-condensable gases accumulate, a layer of steam, known as the steam blanket, may form over the surface, insulating it and preventing proper heat transfer. Number 2 is temperature inefficiency. The steam blanket reduces the overall heat transfer efficiency, causing the surface temperature to rise beyond intended limits and potentially leading to overheating of the equipment. Number 3 is material degradation. Prolonged exposure to elevated temperatures can weaken the structural integrity of materials, leading to potential embrittlement, warping, or failure of components such as piping, valves, and heat exchanger tubes. Number 4 is pressure buildup. The presence of a steam blanket can result in localized pressure increases, leading to the risk of bursting or failure of other components within the system. Number 5 is corrosion. In some cases, high temperatures may also accelerate corrosion processes, especially if residual moisture or non-condensable gases are present in the system. Understanding steam blanketing damage is essential for maintaining safe operational conditions and ensuring the longevity of equipment in industrial processes that utilize steam. Steam blanketing damage affected materials based on API 571, carbon steel and low alloy steels. Steam blanketing is a phenomenon that occurs primarily in heat exchangers, where steam accumulates on the heat transfer surfaces and inhibits effective heat transfer. This can lead to localized overheating, causing damage to the materials involved. The materials affected by steam blanketing damage mechanism typically include: Number 1 is carbon steel. Commonly used in piping and pressure vessels, carbon steel can experience oxidation and degradation at elevated temperatures due to steam blanketing. Number 2 is stainless steel. While more resistant to corrosion and high temperatures than carbon steel, stainless steel can also suffer from localized overheating and thermal fatigue if exposed to steam blanketing. Number 3 is alloy steels. High-performance alloys may be used in critical applications, however, they can also be affected by steam blanketing, leading to degradation of mechanical properties. Number 4 is copper and copper alloys. These materials are commonly used in heat exchanger tubing. The effects of steam blanketing can lead to corrosion or pitting, especially if the steam contains impurities. Number 5 is thermoplastics and composites. In some applications, non-metallic materials may be used. These can be sensitive to temperature increases due to steam blanketing, leading to deformation or failure. Number 6 is insulation materials. Insulation around piping and vessels may also be affected, as high temperatures can degrade the insulating properties and lead to thermal bridging. To mitigate steam blanketing damage, measures such as proper design of heat exchangers, regular maintenance, and monitoring steam quality are essential. Critical factors based on API 571. The first is heat flux and fluid flow are critical factors. The second is flame impingement from misdirected or damaged burners can provide a heat flux greater than the steam generating tube can accommodate. The third is on the water side. Anything that restricts fluid flow, for example, pinhole leaks lower in the steam circuit or dented tubes from slag falls, will reduce fluid flow and can lead to departure from nucleate boiling, DNB, conditions. The fourth is failure occurs as a result of the hoop stress in the tube from the internal steam pressure at the elevated temperature. Steam blanketing is a type of fire hazard that occurs when a layer of hot steam covers a surface, causing the surface temperature to rise and potentially leading to a fire. Steam blanketing is a phenomenon that can lead to significant damage in heat exchangers, particularly those that handle steam and condense it back into water. The critical factors contributing to steam blanketing damage mechanism are: Number 1 is high-pressure steam. High-pressure steam is the primary cause of steam blanketing. When high-pressure steam comes into contact with a surface, it can rapidly heat the surface, leading to a loss of heat transfer and potentially causing a fire. Number 2 is flow conditions. The velocity of the steam and flow patterns can influence the tendency for steam blanketing to occur. Low steam flow rates. Low flow rates may allow for more stagnant areas where steam can accumulate. High steam flow rates. High steam flow rates can lead to the accumulation of hot steam and increase the risk of steam blanketing. Number 3 is inadequate ventilation. Poor ventilation in a system or area can lead to the accumulation of hot steam, which can cause steam blanketing. Number 4 is high temperature differences. Large temperature differences between the steam and the surrounding surface can lead to rapid heating and steam blanketing. Number 5 is thermal load and operating conditions. Variations in thermal load, pressure, and operational parameters can induce conditions that favor the development of steam blanketing. Number 6 is insufficient cooling. Inadequate cooling systems or insufficient cooling capacity can lead to the buildup of hot steam, increasing the risk of steam blanketing. Number 7 is poor design or maintenance. Poor design or maintenance of systems, such as pipes, valves, and vessels, can lead to the accumulation of hot steam and increase the risk of steam blanketing. Number 8 is heat exchanger design. The design of the heat exchanger itself, e.g., the arrangement of tubes, the presence of baffles, and the overall geometry, can impact how effectively steam and condensation interact, thus affecting the likelihood of blanketing. Number 9 is corrosion or fouling. Corrosion or fouling of surfaces can reduce heat transfer and increase the risk of steam blanketing. Number 10 is presence of non-condensable gases. The accumulation of non-condensable gases, like air, can disrupt the condensing process of steam. These gases can create barriers that increase the likelihood of steam blanketing. Number 11 is surface characteristics. The nature of the surface, including material, roughness, and cleanliness, can affect how steam condenses on the surface. Smooth, clean surfaces facilitate better heat transfer compared to rough or contaminated surfaces. These critical factors can contribute to the development of steam blanketing, which can lead to damage to equipment, injury to personnel, and environmental hazards. Steam blanketing affected units or equipment based on API 571. All steam-generating units including fired boilers, waste heat exchangers in sulfur plants, hydrogen reformers, and fluid catalytic cracker, or FCC, units. Failures can occur in superheaters and reheaters during startup when condensate blocks steam flow. Steam blanketing is a damage mechanism that occurs primarily in high-temperature systems where steam can condense and create a layer of water on the surface of equipment, such as heat exchangers, reactors, or pipelines. This can lead to issues such as corrosion, loss of thermal efficiency, and mechanical failures. The units or equipment affected by steam blanketing can include: Number 1 is heat exchangers. The condensation of steam on heat exchanger surfaces can lead to corrosion and fouling, impacting heat transfer efficiency. Number 2 is condensers. Similar to heat exchangers, condensers can suffer from issues like thermal fatigue, localized overheating, and corrosion due to the presence of steam blanketing. Number 3 is distillation columns. Steam blanketing can impair the efficiency of distillation operations by affecting temperature profiles and leading to operational reliability issues. Number 4 is reboilers. Similar to heat exchangers, reboilers that utilize steam can experience blanketing issues that affect thermal performance. Number 5 is pipelines and valves. In systems carrying steam or fluids at high temperatures, condensation can occur, leading to corrosion and mechanical damage in pipelines and valves. Number 6 is process piping. Pipes carrying fluids that are at risk of steam blanketing can experience increased temperatures that lead to stress and failure, particularly in areas of thermal cycling. Number 7 is pressure vessels. Equipment such as reactors and storage tanks where steam may condense can be affected, leading to conditions that might promote localized corrosion. Number 8 is steam traps. Equipment designed to remove condensate from steam systems can become clogged or damaged if steam blanketing leads to excessive condensation. Number 9 is turbines. While not directly related, steam turbines can experience operational inefficiencies if steam blanket conditions lead to lost thermal energy. Number 10 is fired heaters and furnaces. In applications where fuel is heated indirectly using steam, blanketing can occur and affect efficiency and equipment longevity. Number 11 is storage tanks. Tanks that experience steam blanketing can suffer from corrosion and structural integrity issues due to varying temperature and pressure conditions. Number 12 is safety relief valves. These can malfunction if steam blanketing occurs and affects their operation during pressure relief scenarios. The main concern with steam blanketing is that it can create an environment conducive to thermal fatigue, corrosion, and overheating, ultimately compromising the integrity and efficiency of the affected equipment. To mitigate steam blanketing, it's important to control operating temperatures, manage steam quality, and implement design improvements that enhance drainage and minimize condensation effects. Regular maintenance and inspection of these units are also critical to identify potential issues early, as well as appropriate design considerations, are essential to mitigate the risks associated with this mechanism. Appearance or morphology of steam blanketing damage mechanisms based on API 571. The first is these short-term, high-temperature failures always show an open burst with the fracture edges drawn to a near knife edge, see Figure 4.32. This Figure 4.32 showing short-term high-temperature failures from DNB are wide-open bursts with the failure lips drawn to a near knife edge. They are ductile ruptures. Mag. 25X. The second is the microstructure will always show severe elongation of the grain structure due to the plastic deformation that occurs at the time of failure. Steam blanketing is a damage mechanism commonly observed in heat exchangers, particularly those utilizing steam as the heating medium. This phenomenon occurs when steam is unable to fully contact the heat transfer surface, creating a layer or blanket of non-condensable steam that insulates the surface from effective heat transfer. The morphology and appearance of steam blanketing damage can include several key characteristics. Number 1 is localized heating effects. In areas where steam blanketing occurs, there might be signs of localized overheating. The affected surfaces can show discoloration, such as darkening or bluing of the metal, indicating that these regions have been subjected to higher temperatures than intended. Number 2 is surface erosion. Prolonged exposure to steam around blanketed areas can lead to erosion of the surface material, particularly if condensate or other fluids are present. The erosion may appear as pitting or loss of material in the areas where the steam blanket is disrupted or where heat can partially transfer. Number 3 is scaling and deposits. The reduction in effective heat transfer can lead to a buildup of scale or deposits on the heat transfer surfaces. These deposits may appear as white or grayish layers of mineral buildup, which can exacerbate the blanketing effect. Number 4 is cracking and creep. In severe cases, the thermal stresses induced by intermittent heating can cause cracking or creep in the material. This damage might appear as fine cracks or folds, particularly at weld seams or joints where stresses are concentrated. Number 5 is vapor barrier formation. The steam blanket itself acts as a vapor barrier, which can lead to differential heating in the metal. Over time, this can result in thermally induced embrittlement or the formation of stress corrosion cracks, especially in alloys that are sensitive to such conditions. Number 6 is loss of thermal conductivity. The effectiveness of heat transfer can be visually assessed by observing differences in surface temperature or efficiency over time, leading to operational issues in the system. The morphology of steam blanketing damage can manifest as a combination of discoloration, erosion, scaling, surface cracking, and potential loss of material properties, highlighting the importance of proper design and operational practices to mitigate this issue. Regular inspections and maintenance can help identify early signs of steam blanketing and prevent further damage. Steam blanketing damage mechanism is a type of damage that can occur in nuclear power plants due to a loss of cooling or an excessive amount of moisture. The steam blanketing mechanism appears on the surface of equipment as a blanketing or a matting effect of water droplets. Some common features associated with steam blanketing damage include: Number 1 is surface roughening. The surface of the affected equipment becomes rough, due to the formation of water droplets on the surface. Number 2 is rust staining and corrosion. Water and moisture can seep into the gaps between the equipment components and promote the growth of rust, which can lead to corrosion. Number 3 is white or grayish powdery deposits. The formation of water droplets on the surface of the equipment can lead to the growth of a white or grayish powdery deposit, which is typically a mixture of water and other substances. Number 4 is pitting and erosion. Steam blanketing damage can also lead to pitting and erosion of the equipment surface, particularly in areas where the water droplets are most concentrated. Number 5 is discoloration. Affected areas may exhibit discoloration, such as white or grayish patches, due to the presence of water and moisture. In general, steam blanketing damage can appear as a uniform or non-uniform blanketing effect on the surface of equipment, often accompanied by rust staining, corrosion, pitting, erosion, and discoloration. Prevention and mitigation of steam blanketing damage mechanisms based on API 571. The first is when a departure from nucleate boiling, or DNB, condition has developed, tube rupture will quickly follow. Proper burner management should be practiced to minimize flame impingement. The second is proper boiler feed water, or BFW, treatment can help prevent some conditions that can lead to restricted fluid flow. The third is tubes should be visually inspected for bulging. Steam blanketing, also known as steam flooding or steam blanketing of a vessel, occurs when steam condenses on the outer surface of a vessel and prevents it from cooling, leading to an increase in the internal pressure and potential damage to the vessel. Here are some prevention and mitigation measures for steam blanketing damage. Number 1 is prevention. As following. The first is proper insulation and jacketing. Ensure that the vessel is well insulated and jacketed to prevent heat transfer from the steam to the outer surface. This reduces the likelihood of condensation and the pressure buildup. The second is proper drainage. Ensure that the condensate can drain properly from the jacket to prevent it from collecting and causing the steam blanket effect. The third is monitoring. Regularly monitor the temperature of the vessel and the steam surrounding it. If the temperature drops below the saturation point, it indicates that condensation is occurring. The fourth is use of condensate return systems. Implement systems to return the condensate back into the system or a receiver to prevent accumulation around the vessel. The fifth is steam quality. Ensure that the steam used is dry and not wet, as wet steam can increase the likelihood of condensation. The sixth is operational procedures. Follow established operating procedures for handling steam and vessels to avoid sudden changes in temperature or pressure. Number 2 is mitigation. As following. The first is automatic drains. Installing automatic drains to remove condensate as it forms can help prevent the buildup of pressure inside the vessel. The second is cooling systems. If possible, provide a cooling system to reduce the external temperature, thus preventing condensation. The third is steam vents. Installing vents allows for controlled release of steam, which can help prevent an overbuildup of pressure that could cause damage. The fourth is pressure relief valves. Ensure that pressure relief valves are installed and functioning correctly to relieve any built-up pressure within the vessel. The fifth is regular maintenance. Regularly inspect and maintain the vessel, its insulation, and any related systems to ensure they are in good condition and functioning as intended. The sixth is operator training. Ensure that operators are trained in recognizing the signs of steam blanketing and know how to respond appropriately. Implementing these prevention and mitigation measures can significantly reduce the risk of steam blanketing damage to vessels, ensuring safer and more efficient operations in industries such as power generation, chemical processing, and oil refining. Inspection and monitoring for steam blanketing based on API 571. Burners should be properly maintained to prevent flame impingement. Steam blanketing damage can be detected using various inspection and monitoring methods, including Number 1 Visual inspection. Regular visual inspections of the boiler or heat exchanger can help identify signs of steam blanketing, such as rust, corrosion, or pitting on the surface. Number 2 is thermal imaging. Thermal imaging cameras can detect temperature differences in the boiler or heat exchanger, indicating areas where steam blanketing may be occurring. Number 3 is ultrasonic thickness measurement. Ultrasonic thickness measurement can be used to measure the thickness of the boiler or heat exchanger tubes, detecting any signs of thinning or corrosion caused by steam blanketing. Number 4 is acoustic emission testing. Acoustic emission testing can detect the high-frequency sounds emitted by steam blanketing, allowing for early detection of the problem. Number 5 is corrosion monitoring. Corrosion monitoring techniques, such as corrosion coupons or electrochemical sensors, can be used to detect the corrosive effects of steam blanketing. Number 6 is conductivity measurements. Conductivity measurements can be used to detect changes in the electrical conductivity of the water, which can indicate the presence of steam blanketing. Number 7 is pH measurements. pH measurements can be used to detect changes in the acidity of the water, which can indicate the presence of steam blanketing. Number 8 is oxygen scavenger testing. Oxygen scavenger testing can be used to detect the presence of oxygen in the water, which can contribute to steam blanketing. Number 9 is heat transfer coefficient measurements. Heat transfer coefficient measurements can be used to detect changes in the heat transfer efficiency of the boiler or heat exchanger, which can indicate the presence of steam blanketing. Number 10 is non-destructive testing, or NDT. NDT techniques, such as radiography or magnetic particle testing, can be used to detect internal damage or corrosion caused by steam blanketing. Number 11 is boiler water analysis. Regular boiler water analysis can help detect changes in the water chemistry, which can indicate the presence of steam blanketing. Number 12 is vibration analysis. Vibration analysis can be used to detect changes in the vibration patterns of the boiler or heat exchanger, which can indicate the presence of steam blanketing. By using these inspection and monitoring methods, steam blanketing damage can be detected early, and corrective actions can be taken to prevent further damage and maintain the efficiency and reliability of the boiler or heat exchanger. Thank you.